We are now on the topic of the hydrostatic pressure, or the pressure that water exerts on a submerged surface. So the submerged surface can either be regular in shape or it could be irregular. So the pressure then will be dependent on the area of this particular surface that is submerged in water. So the thing that the term hydro means water, hydrostatic meaning it's not the pressure that is exerted by water that is not moving on a submerged body. Okay, but first we're going to look into our learning objectives. So there's a need for you to know what the hydrostatic force is, and we need to use the integration in determining the hydrostatic force or the hydrostatic pressure. Now, what is the hydrostatic force and pressure? So the force that is exerted on a plate due to the pressure of water is called the hydrostatic force. So I have mentioned that already. Hydro meaning water. So what is the force that water is exerting on a particular object or material that is submerged? So in the definition here, the material is a plate. Now, you have the illustration here on the right side. So forces on submerged surfaces, in this case, we have to use vertical wall integration. So for this particular wall that you could see, the wall has width W, it has a height H, and the height of the submerged surface or the surface of the wall which is subjected to this hydrostatic force is varying depending on the particular part of this surface which is completely submerged in water. So the height is dy because it depends on how much of the entire wall is submerged, and this is dA. dA, the differential area of this particular strip, it's dA, it's changing, it's varying because the dy is also changing. Okay, so in here we have force as defined as the product of the pressure and the area. Okay, this hydrostatic force, which is unknown, is the product of the pressure and the area. Now, working out from this equation, another equation determining the pressure given the force, so that would be this one. So you keep the pressure on this side of the equation and you divide by A. So pressure is equal to the force divided by the area. The thing is, the reason why pressure is changing, it's because the area is also changing. In this formula, the only thing that is constant is the force. So the force is constant because that's equivalent to the action of gravity. We have here in the formula for pressure, the action of gravity on the body, rho GD. Okay, so the force is fixed, however, our area is changing. So in the process, since we have a varying area or changing area, the force will also vary. So you can see this area is equal to the W, the width of this wall, times the dy, this particular height of this particular differential strip. So that's dy, W dy. So dF is equal to the pressure times the dA. So where is this coming from? It's coming from the original formula. dF, the changing force or hydrostatic force, is equal to the pressure, which we will compute using the formula rho GD times the changing area. If this D that has something to do with the Y is not changing, this pressure will have been varying as well. But in this case, we fixed it. It's something that is fixed. So now we have this particular differential equation because it has the presence of the differentials that we will need to integrate. That way, we will determine the hydrostatic force based on this dy here, the dy of this differential strip. So it's equal to rho GW dy. Rho G Rho G is this rho G, and then the D, the W, and the dy. Okay, now you may wonder why you have pressure change here to rho. By the way, class, this is G sub y, the gravitational constant, which is oriented vertically. So the G here is actually the subscript, no, the y is the subscript of the G. Okay, so you have rho G sub y W, W is this, dy. Okay, the height of this differential element. But let's look into the pressure, the hydrostatic pressure, because we change the pressure term here in terms of the y. Okay, the pressure in terms of the rho GD, which is now having the presence of the y. So first, if we are d meters below the surface, so if this particular wall is d meters below the surface, then the hydrostatic pressure is given by the product of the density, the rho that I'm talking about is the density, the G, the gravitational constant, and the D, the, shall I say, the height of, it's not the height of the water, but rather that part of the wall which is submerged in water. Okay, so that's the D here, the rho GT. Now it's defined. Density G is the gravitational acceleration. We're going to assume that the fluid in question is water since we're talking about hydrostatic pressure. And since we're going to be using the metric systems, the quantities become, so this is to be memorized. The density of water for this topic is 1,000 kilograms per cubic meter, and the gravitational constant is 9.81 meter per second squared. Now assume that a constant pressure is acting on a surface with area A. So let's assume that first this pressure is constant. Then the hydrostatic force that acts on the area is this one. This is the hydrostatic pressure. I'm referring to this P. And this is the hydrostatic force F. And you could see here in the left side, the formulas that I have mentioned a while ago. The main equation that we're going to process, that way we can determine the hydrostatic force, is the last one that you see in here. T sub F equal to rho Gy W dy. Okay, something to do with this one. So rho G, the D, by the way, here is the Y, which I said to be the vertical orientation of the wall, something to do with the vertical orientation of the wall. You can see here the Y as this one, the height of the wall that is submerged in water. W is the width, and dy is this differential, the height of this differential area. Okay, now we proceed. So we'll have this example one because it's quite difficult to cross the entire thing if we don't talk about a specific example. Now you are asking here to determine the hydrostatic force F on a triangular plate that is submerged in water. So this is your triangular plate. The width of the triangular plate is 6 meters, and it is having a height of 4 meters. And this is the water surface. So meaning the entire triangular plate is submerged in water. The first thing to do here is set up an axis. So you have to set up an axis right on this particular triangular plate. So let's redo the sketch above. So the sketch is placed on the Cartesian plane, or that is your axis, the x and y axis, with the system like this. The water surface coincides with the x-axis, and the middle part, or like on the tip of this triangular plate, that's the middle part of our triangular plate, is right on the vertical axis. Now in here, we're so used, class, we're so used, even myself, I'm so used that we represent the vertical axis as y, and we have the horizontal axis as x. In this case, class, we have this as x, not I, and in here would be any variable that we want. What is important is this vertical distance from the water surface down of your submerged triangular plate is x, not y, because in the next part of the solution is represented as x as well. So this one, for this, it's immaterial. You can use any letter that you have in mind as to what would be your labeling here for the horizontal axis. But the vertical axis is represented as x. Now we will proceed. So we are going to orient the x-axis so that the positive x is down. So again, another contrary to what we have learned, we know that downwards means negative and upwards means positive. But take note, it says here that it's going to be that the downward direction for the x is positive. Positive x is downward. X equal to 0 corresponds to the water surface. So this is where your water surface is. This is your x equal to 0. And x equal to 4 corresponds to the depth of the tip of the triangle. So the tip of your triangle is this one, and this entire thing, so the labeling is very small, is 4. Okay? From the surface of the water up to the tip of the submerged triangular plate. Now we break up our triangle into horizontal strips. So these are the horizontal strips that are being referred in here. You get to only see one horizontal strip emphasized in here. So in this triangle, you will have several horizontal strips. Now each of which have equal width of delta x. So this one is delta x. So the way we divide our triangular plate into these horizontal strips, they have the same width, delta x, or another term probably is thickness. If you view this one as the thickness, so it's delta x. And in each interval, you have x sub I minus 1 and x sub I. Choose any point x sub I asterisk. Now, the x sub I asterisk will represent it like this. So, from there going down until only here, that's your x sub I asterisk. Okay? From the surface down to the horizontal strip that we have drawn. In order to make computations easier, we're going to make two assumptions about these strips. So, about these strips that we have, we are to make two assumptions. Number one, first, we will ignore the fact that the ends are actually going to be slanted. Now, if you're going to look closely here, even not so closely, this will not be true and true rectangular, because in this part in here, it will be slanted. But you're going to assume that these strips are so small that it will not be that way. So it will not be slanted, but rather it will be one horizontal strip in which the sides are vertical, not slanted. Okay, that's the first assumption. They are actually slanted, but we will assume that they are rectangular. If delta x is sufficiently small, this will not affect our computations much. So I have mentioned that. The second assumption, we will assume that delta x is small enough that the hydrostatic pressure on each strip is essentially constant. So meaning, the second assumption tells you that the manner you divide this particular face of our triangular plate into horizontal strips, this particular delta x is made sufficiently small that the hydrostatic pressure applied in the plate in this region would be the same in this region. Okay? If delta x is sufficiently small, this will not affect our computation that much. We will assume that delta x is small enough that the hydrostatic pressure on each strip is essentially constant. This is irregardless of where the strip is. Okay, the assumption that it is small enough or thin enough that pressure is constant. Now, the height of the strip, which is delta x, so this one, this horizontal strip is delta x as I have drawn, and the width is 2a. So 2a, this width. Okay, the entire thing is 2A. We can use similar triangles to determine the A as follows. So I'll draw here two triangles. Okay, I have one triangle here, which corresponds to half of this triangular plate, the original. So it has, wait, why is it 3/4? Let me check us, ha? Maybe it's given here. Okay. Okay. It's not stated in the problem, but the way it's drawn here in our solution, this particular half length of our triangle, or half of the base, not that, half of the base of the triangle is 3. So I'm taking the triangle that I have drawn here is this one whole thing. Okay, I'll draw this one. So this is the triangle that I am drawing. So this is B as drawn here. So it's not mentioned in the problem. That is why I was not able to get it at start. And we have here 4. That's the entire. Now, if you have a small triangle, you take out the small triangle where your strip lies on. This is the big triangle. This is the small triangle. They have to be similar because they have the same angle here. Whether you have a big triangle or a small triangle, the angle here is the same. So what is this one? So if we will represent the width of this rectangular strip is 2A, then this must be A. So that is why you could see here A. So this is A. And what about this one? If this thing was labeled a while ago as x sub I asterisk, the remaining part of this one would be the entire length minus the x sub I asterisk. So you have 4 minus x sub I. So this is 4 minus x sub I asterisk. Now, if you now want an equation that will relate A to x sub I, the location of this particular horizontal strip in our triangular plate, then it would be by means of similar triangle. So 3 is to 4 equal to 3 is to 4 equal to this one. The 3 is equivalent to A in our small similar triangle to the big, and you will have here 4 minus x sub I asterisk. Now, you want an equation for A as a function of x sub I, or asterisk, or simply x later. So then that would be requiring that A would be 3/4 times 4 minus x sub I asterisk. If you do expansion, A is equal to 3 minus 3/4 x sub I asterisk. And that equation is this one. Now you may wonder, why the need to set up an equation relating the A, half of the base of the small triangle, which represents the whose base rather is represented by this rectangular small strip. Okay, why? Why the need for A in that matter to be expressed in terms of x? Anybody? Why need this equation? Why look for this equation that will express A as a function of x sub I asterisk? The location of the differential area from the surface of the submerged triangular plate. Why? Why express it in terms of x? Okay, you need to express it in terms of x because when you integrate, you don't have dA. When you integrate, it will be in terms of dx because what varies here is the width of this particular rectangular strip, whose width is deemed constant even though not. Okay, we assume to be not slanted although it is slanted. Okay, wala kasang hindi ka pwede kagamit sang A because when you set up your integration later, you don't have A, but rather what you have is dx because of this delta x. So you need to express A in terms of this x here, okay? Since you have delta x as your differential. The second reason behind class is of course the fact that this A varies. The A in this part here is different here. So there has to be an equation that should relate this varying A in terms of this x sub I asterisk, which is the location of the differential area as placed on this triangular plane. Okay, so you have now the A. Now what will you do with that? So we will clear our markings here. So I hope everybody sees the importance of having to get the A. I go to the next slide. Now, since we are assuming that the pressure on this strip is constant, the pressure is given by rho GD. This is your rho. This is your density, the rho. This is your G. And this D class, rho GD pressure, the D is the height of the differential element or the distance of the differential element, the differential area from the surface of the submerged triangular plane. This is it. This is your X from here up to here. Okay, this is the location of this rectangular plane. So that is why you have your X sub I asterisk. So now your pressure, which is constant, is represented in terms of X sub I asterisk, which tells you of the distance of this differential area or strip from the surface of the water. Okay, but then we know that hydrostatic pressure is the product of, rather hydrostatic force is the product of the hydrostatic pressure and the area. So you have pressure here. What about the area? Isn't this one A? This is A. So then this must be another A. So 2A. A plus A, you have 2A. This one we have represented to be delta X. So you have here delta X. So this area that appears in the formula for the hydrostatic force is the area of this rectangular strip, or it is the differential area. So you have the area now. Okay, so you have this one as the area. Then you just copy the pressure here. So 1000 times 9.81, so that's 9,810 x sub I asterisk. You have the 2 from here. What is this A? The A is the A that we got in the previous page. So I hope you were able to get it. The A is 3 minus 3/4 x sub I asterisk. This time, A is expressed in terms of the X. Okay, so this is your 2, this is your A, and this is your delta X, and this is your P. The entire expression that is. So P times A is equal to hydrostatic force. That's F. So if you do the mathematics, you have this multiplied by 2. That would be 19,620 x sub I asterisk. This one was just copied, and you have here delta S. Now, using the definition of the definite integrals, and there's just nothing more that we can write except that the hydrostatic force, when integrated, this is dF, is equal to this one. All of this you copy. You change the delta X to dx. Since you are determining the hydrostatic force from, so this is 0 actually, and this is 4. So you are determining what would be the pressure in here. So if you want only to know the pressure up to 1, let's say 1 meter, if this is in meter. So 1 meter below the surface, so that would be 0 to 1. Since we are determining the hydrostatic force from here from the surface up to the tip of this triangular plate, you use the limit 4. So you change the upper limit of this integral depending on the hydrostatic force that you want to know in terms of location. Let's say, for example, you want to know the hydrostatic force in here. So, of course, your limit will not be 0 to 4 because this probably is just based on our orientation. This is 4 and this is 2. This is just more or less 0.8. So, then your limit will be from 0 to 0.8 because you just want to know the hydrostatic force up to this part, not the hydrostatic force up to the tip of the submerged triangular plate. So, that is why you have your limits here starting from 0 because your x here is 0 until, of course, it's 0. It's positive x as we go down. So, this is 4. That is 0. So, that is why you have until 4. The rest, of course, is just very simple math because all you have to do is multiply and use power rule. In this case, for this entire triangular plate, the hydrostatic pressure is 156,160 Newton or 156.96 kilo Newton. Now, we had the dx here coming from the delta x for just one strip, but you have several strips here. So, the hydrostatic force that you are computing depends on up to what particular point you want the hydrostatic pressure measured. So since you want the hydrostatic pressure on the entire plate, then this would be your limits. Any questions before we go to the next problem? So remember, the force is equal to the pressure times the differential area. Actually, this is dm. So if you integrate and integrate, you drop the d there. So you will have F equal to P dA. So the reason why you express the pressure in terms of x sub I asterisk, it's because your dA here will be expressed in terms of x. Now, do you have any question? Any question? Wala question? O akong mamangkot, what is this area here that I've checked? This is the area of the what? Since you are not asking question. What is this area that I have checked? So pressure is kept constant but expressed in terms of x. What is this area in the first place that we are interested in determining the hydrostatic pressure applied on it? So what is this area? It's the area of the what? Oh, wala ka mga pamangkot. Ako na mangkot, wala man ka mga sabat. So, it tells me that you don't follow through the explanation. Let's see. Area of the triangle. In particular, if you're not yet integrating, what is this A? Just this A. Of course, if you have integrated already, that would be the area of the triangular plate. But this A in particular, as written in here, without yet the integral symbol, is just the A of the what? Just the A of the pinuwas kay JB, sino pa da? Okay, very good, Renan. It's the area of the differential strip. It's the differential area of the strip. JB said saying, Miss, ang area, iyan na isang triangular plate. True, because nag-integrate ka na from 0 to 4. But if you're just interested on determining, let's say, for example, the hydrostatic pressure until here, then the summation of these differential areas of the strips that you use in dividing this triangular plate, hasta lang daig, hasta lang ang gusto mo. Pero kung ang entire nga triangular plate, you use the limits 0 to 4. So that is very good, Renan. Ang A nga ini, iyalan na initially sang strip. But if it's integrated already, the area that in question is the area of the entire triangular plate, because in the first place, everything is submerged, or your entire triangular plate is submerged. Okay? So pressure expressed in terms of X sub I, because pressure is rho g d. What is this d? This d is the measured distance of the strip or the differential area from the surface of the triangular plate. Okay? So you are determining sa aton language pila ang pressure hasta diho. Diri lang halin di pakadto di. So that has something to do, or it needs the x here, whatever that x may be. But if you intend to determine the pressure on the entire plate, then this is the one that you use. So express it in terms of X sub I and integrate it from 0 to 4. Okay, I have a question. Miss nga agani ang 19,620 X sub I. Wait. Okay, Ario, 9,810 times 2. So that would be your 19,620. Then, gin-affix ng si X sub I kay variable na siya. You get it? Your 9,810, this one, times 2. May multiplier siya nga 2 kay base sa aton nga formula. You have pressure times twice of A. So T, this is your 2 and this is your A. And this is your delta X. I hope that answers your question. Okay? Sige. Paay na pamangkot. You go to the next. If there are no more questions, we go to the next. I'll wait. We'll clear this part first. Now we go to the next. The first one is a triangular plate. This one is circular. So find the hydrostatic force on a circular plate of radius 2. So that this one is of radius 2 that is submerged 6 meters in the water. Submerged 6 meters in the water. Look at the interpretation of submerged 6 meters in the water. Meaning this side of the circular plate is 6 meters below water. The radius of this particular circular plate is 2. So we only have 2 specific given information. The depth in which the circular plate is submerged and the radius of the circular plate. So first, we're going to assume that the top of the circular plate is 6 meters under the water. Okay, it's here, 6 meters in the water. So the top portion is 6 meters below the water surface. Next, we will set up the axis system so that the origin of the axis system is at the center of the plate. So this is your X, this is your X, and this is your Y. Here on the center, you have 0. This is 0. Finally, we will again split up the plate into n horizontal strips, just like what we did with the triangular plate. You're going to cut your circular plate into very thin rectangular strips. thin enough that way you can assume that the side of this differential area or strips will be also vertical, not curved or not slanted. Okay? Each of width delta y. So in this case, class, the width kay na ang aton, yung width delta x, kaya ang aton vertical axis x. So buong kay we went with the original orientation, which is x for horizontal and y for vertical. So this width of our strip will be delta y or dy. It says here, split up the plate into n, meaning n, several, n horizontal strips each of with delta y, and choose a point y sub I asterisk. It's the same as the one we have. So the distance from the water surface to this strip is y sub I asterisk. And we'll choose a point y sub I asterisk from each strip. Oh, by the way, this y sub I asterisk is not measured the way it was measured in example 1. I stand corrected, class. It's not like that. Your y sub I asterisk is from this point, just annotate. From this point here, the center of our axis is on the center of the circular plate. Its distance, the distance of this strip is y sub I. So this one, it's so small, probably you won't be able to see it. That's your y sub I. Not from here going here, but from the 0 point here for vertical orientation going up. That's y sub I. Okay? Says here, and we'll choose a point y sub I asterisk from each strip. We'll also assume that the strips are rectangular again to help with the computation. And that's the sketch that we need to look into. Okay? Now, I'll proceed to the next slide. Oh, sorry. Now, the depth below the water surface of each strip is. So, if this is x sub I, or rather y sub I, I've done it a while ago, and this entire thing is 8. By the way, I would like to ask you, why is this entire thing here 8? Was that stated in the problem? Why is this 8, if I may ask you? Come on, think. Why is this 8? It was not
Yes.
mentioned in the problem. Yes?
Kaya ang radius may isang circle is 2
And
lang. Tapos nakasubmerge sa may 6 meters or units from the water.
is.
So 8 plus 2.
That's correct, Renan. So, di ba gin-assume ta nga ang pag-mention sa problem that it's submerged 6, 6 meter or 6 feet below the surface of the water. So, this edge of our circular plate is 6 meters or feet below the water surface. And since this is 2 meters or 2 feet, then the total is 8. Okay? That's 8. So if you want to represent the depth below the water surface of any of the strips that you will draw, this depth here, d sub I, that would be dependent on the y sub I. The y sub I is measured from the center of your circular plate. So your 8 minus y sub I is the distance in which this strip is submerged in water. We're referring to the distance of this particular strip from the water surface since it is submerged. So this is it. The depth below the water surface of each strip is 8 minus y sub I asterisk. And that in turn gives us the pressure on the strip. So pressure, what is pressure? Rho G di. Pareho man kaina. So what is this rho GDI? Rho is 9,810 raw G. So your raw is 1,000, your G is 9.8, so that would be now 9,810. By the way, class, raw G na ini siya, si 9,810. Because of the fixed density of water, which is 1,000, multiplied to the gravitational constant, which is 9.81. So ining 9,810, amo na ning products ng duha, the raw G. The D sub I is the distance of the strip from the water surface, expressed in terms of Y sub I asterisk. Again, wonder, why is it expressed in terms of Y sub I asterisk? It's because this one is not able to annotate. The thickness or the width of your differential area or strip is delta Y, because this is your y-axis. So there's a need for you to represent the D sub I in terms of Y. Okay, so you have this one now. By the way, I have transferred already. Wait, class. I close my marking. I transferred to here. So I'll go back here. So in here. Okay, so since this one is delta Y. Okay, now the area again, this area is the area of the strip. So what's the area of the strip? It's twice of the square root of 4 times y minus I asterisk squared. Now question, how did this particular thing came about? The square root of 4 minus y sub I asterisk squared. Di na siya naghalin man, this one. Can somebody tell me where this came from? So you have the delta y, you have this one, and it's multiplied by 2 because you're determining the area of the entire strip. So the question now is this, the big question mark, where did this came from? Because you have 2, this is the width of your strip, which is delta y. What about this? Where do you think did it came from? It has the square root. Where did it came from? You, as a hint, you should think of the square root. May square root siya ho, so di na siya naghalin. Where do you think did it came from? Okay, I'd like you to think. Whoever can give me the answer will have plus 10 in the exam. Because we don't have any more quiz. So you will have plus 10 in the exam. Think, how did the square root, or where did the square root of 4 minus y sub I asterisk came from? Plus 10 in the exam. And your clue there is it has the square root. Ano may mga square root man? Nga may square root. Dason squared sa sulod, oh. I give sang maklaim sang plus 10. 1 minute.
Miss,
Let me.
is it miss, part sang hyperbolic and inverse hyperbolic function?
No. Hindi siya
Okay.
related ho sa hyperbolic and inverse hyperbolic. Ang clue is ang square root. Tama lang kita nyo na ara na ang clue. Kung diin niya naging kwa na siya. This is x. This is delta y. So this is the area of just this face. It's multiplied by 2 because we have this 2. Ang big question mark is di na siya naghalin. Okay? You cannot place here x because your differential is in terms of y. So you cannot integrate if your variables are not the same. So ang question, diin na siya naghalin. Cx equal to 4 minus y sub I asterisk squared. Okay, may nag-answer na isa. Na-try siya. Then, let me see. Excuse me. Keep on burping. Ang tunga sang deafness below the surface. No, it's not half. It's not half. It has nothing to do with that. I'm asking why your x is square root of 4 minus y sub I asterisk squared. Okay, last 10 seconds. Sige, we'll explain it, ha? So this is it. Use a different color. Pagpipisin orange. Sige. Now, I will make, this is a circular plate, so meaning from here, yes. What's the radius? It's 2, right? Okay. I'll clear first my marking so I can go to the previous slide. The radius is 2. 2. So I go there. So then we have here, this is 2. Here, this is also 2 because that's the radius. That's from the center of the circular plate outwards, that would still be 2 length units. Now, I will do the same in here. This is my strip. I'll make a radius here. This is 2, right? Now, I will have a triangle here. Right? So, my triangle now looks like this. Wow, ganda siya para makita niyo. And we are interested in this side, the x sub I. If this is the radius and this is 2, and this one, the distance from the center to the strip is y sub I, what do you think what was used?
Pythagorean, Miss.
Correct. Correct. All right, triangle. So y sub I squared plus x sub I squared is equal to 4. I want this one. So x sub I squared is equal to 4 minus y sub I squared. I want x sub I. X sub I is the square root of 4 minus y sub I squared. So that's the reason why your 2 times x sub I times delta y is now like this. Do you follow? So that's the reason why you have square root of 4 minus y sub I asterisk squared as your x sub I. You already have the area and your pressure is already expressed in terms of y sub I. So you just multiply these two. The pressure and the area is equal to the force. So 9810 times the quantity 8 minus y sub I asterisk and multiply to this entire thing. If you want to know the hydrostatic force, that would need you to integrate. You need to integrate the hydrostatic force acting on this entire circular plate submerged 6 meters or feet below the water surface. So what was done is this. Bilog ni siya in integrate. So ini ini kay constant man na sila, pwede mo i-multiply. So, and then place it before the integral. And this one together with this and this, you have this and this. The delta y is changed to dy. Look at the limits of integration. Huh? Look at the limits of integration. It's from -2 to 2. Why is that? Why is it from -2 to 2? Because the center of your Cartesian plane is here. So if the if the circle has a radius of 2, so this must be -2. This would be +2. So that's the reason why your integral has these limits. -2. You get it? The rest is just mathematics. You do your maths here. Actually, even if you don't do your maths here, since this is a definite integral, it has limits, your calculator can finish it up for you. All you have to do is place it in your calculator, supply the limits, you will have the answer. But nonetheless, let's say for example, you are living in a time wherein in our time, we have to process this without our calculators because we don't have yet your calculators then you have to recall the techniques of integration that you have used. That way you can have this evaluated. Okay, now I'll clear my markings. Then we proceed to the next slide. Now you have this one. The first integral requires the trigonometric substitution. So this is already class multiplying or introducing. Okay, wait. That's the first integral. You have this. Okay, 19,620 times 8 is just a constant, and you have this. So you will have trigonometric substitution. The second one is 19,620 times y times this. Okay, this one. So the first integral requires trigonometric substitution. The second integral requires the substitution. The v or the u is equal to 4 minus y squared. Now this is these are topics which have been discussed to you already. Just in case you will be required to present the complete solution, not just the final answer for the definite integral. So these are the techniques that you should be using. Okay, trigonometric substitution, and this one is just algebraic substitution. Okay, and that's it. You have any questions? And sige. We'll just have a very short 5-minute break. Then we'll go to multiple integrals. Anyways, it's just the process that I will discuss because we'll not have the application covered. Okay? Sige. We'll have a 5-minute break. Then we'll have the last topic. So I will now share my screen on multiple integrals. Can you see the screen already? Is it in slideshow?
Yes, miss.
Okay, multiple integrals. So in here, we will not cover the application anymore, but we will just limit on our discussion on the evaluation of the double and the triple integrals and the properties associated with the said evaluation. Okay. Double integrals in terms of their applications are used in determining the area. So the double integral is used to integrate over a two-dimensional region, and as such, it's limited only to area. And the way it's written, it's like this, meaning you are determining the area of a particular region. Okay? That region is represented by D. This f of x and y simply is to be understood or interpreted as a function which does not only have the x variable, or the y variable, but it has both the x and y variables on it. And the dA here represents the differentials. I say differentials because the differentials that you will be seeing here will also be in terms of the variables that appear on the function. And since in here you have x and y, so you will have dx and dy, okay, for the dA. So this is just a general representation of the two differentials. Now, let me proceed. So for example, you are given this particular double integral that will determine the area of this region bounded by the red and blue curve. So it's the green region here. Now you could see that this double integral that will determine the area of this region is actually equivalent to this double integral. You have the function, whatever the function is, representing these two curves that represents the boundaries of the green region. So that would be the function equation here. You have dy dx. So two differentials. When you do your evaluation, you do it from the inside going out. So meaning the first integration process will be based on the y variable. Whatever variables you have here like x and y, your first integration will be in terms of the y variable, and you will consider the x variable as a constant. When you have your answer already, you substitute to the y variable only these two limits, whatever these limits may be. After that, that's the next time that you do the second integration. You integration lastly in terms of the x variable. After that, you substitute the limits a to b. That would then represent the area of this green shaded region. Just for a moment, class. Okay, so that's it. Now we go to the next. Now, okay, let me just clear my markers. Now, if this is the region that we want to determine the area of bounded by the red and the blue curve, so this is the area that we want to determine, we have this double integral to represent the area of this region. So whatever is the corresponding function equation for this particular region in green, you integrate it in terms of dx and dy. So first, in terms of x variable, y is considered as a constant. Substitute the limits to dx, and then in the second integration, you will integrate in terms of y and substitute c to d as limits on the y variables. So this is a generic representation on how you go about evaluating multiple integrals. And so far, I have shown to you the double integral. Now, before we go into the specifics of how we do evaluation multiple integrals, these are the properties that you need to understand regarding multiple integrals. If you have two functions or your functions have several terms, when you do double integration or even triple integration, you can evaluate per term or you can evaluate per function. So you can see here first, you have the double integral of the function of x and y. Then you add to that the double integral of the g of x and y. So it's just like you separated the double integration process for this expression. It's the same thing when you do just one evaluation, meaning you're not given a multiple integral. Now, if you're given a constant in your function, in your double integral or triple integral, you can set aside that constant, meaning you write it before your integral symbol, and you just process the double integration process, the integral, and afterwards, you just multiply your answer here by c. C is any constant. Now, if your region, the area of the region D can be split into two separate regions, D sub 1 and D sub 2, then your integral can be written as, so it could be the area of the first region D sub 1 plus the area of the region D sub 2. That would then represent the the total area of the two regions. That is, if the area that you are determining can be split, or it's composed of, uh, or that shall we say it's an irregularly shaped area, and you can say that it's composite, and you can break it down into two simple areas which you can easily evaluate. Uh, Please don't confuse me when I say areas that you will have to set up your area equation. No. Here, on this last topic, you will just simply be asked to evaluate. But in terms of application, that's just the way I am explaining it. If you have a composite area, you can break it down into two simple areas, and get individually, separately, the areas using the double integration process indicated, the appropriate double integration process indicated, and then add the answers. And that would represent now the area of your composite region. Now, example in here, because this are I would like you to really focus on the specific example. Your function is e raised to x over y dx dy. So your first integration process is in terms of x. So the y here is considered as a constant. And you can only integrate the EU if its derivative is with it. So let's say, for example, you will have e raised to, I will change the y into any constant so you can understand. So x over a dx. So I can only have this integrated if I will have the derivative of my u, which is 1 over a. So I will multiply here by 1 over a, and I will have here a outside. So in the process now, I can write a e raised to x over a. Then whatever are my limits here, then I'll place in here. So in this case here, you have y and y cubed. So since a is y, I will just have y e raised to x over y, and then substitute the limits y to y cubed. I hope you can follow. The y is a constant, so you can see that this is the answer, the one I've written here, based on what you've learned regarding the integral of the exponential function. And you substitute the limits y and y cubed to, since you are integrating in terms of x to x, not to y. So what happened now is this. Prior to you doing the second integration, you first substitute y and y cubed to x. So if you do that, amo ni siya class ang y is equal to, for the upper integral, you will have e raised to y cubed over y. For the lower integral, a lower limit, you will have e raised to y over y. So here you have y times e raised to y cubed over y is y squared. And e raised to y over y is 1. So e raised to 1. So that's the thing that you're seeing there. Okay? You first substitute the limits to the variable that was integrated before you proceed to the next integration. Then this time you evaluate also this particular integral. So evaluation of this integral requires that the derivative again of the u here in your exponential function should be complete. It should be 2y dy. You already have a y here, so you place 2 and you place 1/2. So 1/2 e raised to y squared. The integral of this will simply be power rule for the y. Your e raised to 1 is a constant, so y squared over 2. Your limits are 1 and 2. So just substitute to the y 2 first, so it would be e raised to 4. And then for here, for the second part, substitute tanay para makita nyo. E raised to, so if it's 2, that would be 4 minus 1/2 e raised to e raised to 1, and then you have here y, which is 2 squared. This is for the upper limit. For the lower limit, you will have 1/2 e raised to 1, and you have minus 1/2 e raised to 1, because this is 1. So this just 1/2 e raised to 1. The entire thing here is 0. So you are left with this one. So you have 1/2 e raised to 4. And you have here, this is squared. So that would be 4 divided by 2. So that would be 2. So 2 e raised to 1. So that's the thing that you are seeing here. You get it? You do the integration process one at a time. First, in terms of the first variable x, and to your answer, substitute the limits in that particular integral to the x variables because you have integrated in terms of x. Then you do the next integration. This same procedure also works when you're dealing with multiple integrals like triple integral. Okay, so this is where you will be reviewed again on the techniques of integration you've learned in midterm. Any questions here? Okay, sige. We'll proceed to the next. So that's your double integral. So let's say, for example, you have this integral 4xy minus y cubed dA. Your limits are square root of x and x cubed. So this particular region, this region is represented by the answer, or the answer is represented by this double integral. The dA is dy and dx. Okay, and you have here already the limits. So what you do, you first integrate in terms of y. So if it's in terms of y, x is a constant. You use power rule here for the y. That would be y squared over 2. So you will have a resulting expression of 2xy squared. This becomes y to the 4th over 4. And then you substitute the limits x cubed and square root of x to y. So your y here will be square root of x. This is square root of x squared for this one. And since you have the x, so that would be now x squared. And in here, you will have also square root of x minus, this time you substitute the limit x cubed. Now, I will illustrate how this came about so it will be clear to you. I will just transfer here below. Okay? I think there's no problem as to evaluating that in terms of y because your first variable is y. When you substitute the limits, I'll just place the limits first. It should be 2x, okay, 2x, no? Your y squared is square root of x. So square root of x squared. Now minus 1/4, and that would be square root of x for the y raised to, sorry, this is in terms of y, correct. So raised to 4. What I have so far substituted, guys, is just the upper limit. Upper limit is square root of x pala ang na-substitute ko sa variables na y. I haven't yet substituted sa lower limit. So you do the same. 2x, this is x cubed squared. Your y squared, your y is x cubed, it's squared. So that minus 1/4 x cubed raised to 4. Okay? Now, this is x times x, so that would be 2x squared. This is x squared, so I will have x squared over y, because that's 1/2. This one is x raised to 6 and 7 minus 2x raised to 7 minus minus, that would be plus x cubed raised to 4, so that would be 12. X to the 4th, x to the x raised to 12, because it's 4 times 3 divided by 4. Do you see your answer here? It's 2x to the 7th plus 1/4 x. Okay, wait lang. This is correct. In here you have, why did I not get the answer here correctly? This 2 is correct. Minus 2x raised to 7 plus x raised to 12 over 4. For this one, you have 2x square root of x y squared minus, okay, so this is the error. I placed y, it should be 4. So we have 1/4. In this case, this is x and x, 2x squared, and this is x squared over 4. 2x squared minus 1/4, that would be 2 and 3/4, and that would be this one. You can combine these two, right? 2 and, or 1 and 3/4 rather. So 1 and 3/4 x squared, which is equivalent to 7 over 4x squared. And then minus 2x to the 7 plus x raised to 12 over 4. Okay, this 1 and 3/4 x squared is coming from here. The 2 minus 1/4 is 1 and 3/4. And then you write this an improper fraction. You have, if you write it in this manner, 7 over 4x squared. Then you will integrate for the last time in terms of x. So initially integrate in terms of x. That would be simple power rule. Okay, power rule. And then substitute the limits 0 to 1. So automatically, if it's 0, you don't need to substitute the lower limit because anyway it's 0. But for 1, you just substitute 1 for the x here for your answer. So your final answer is 55 over 156. Okay? Can you follow, class? It's just integrating several times. You just integrate starting from the inside, the first differential, then you go outside, outwards. When you integrate in terms of one variable, the other variables are considered as constants. Before you do the next integration, substitute first the limits, then do the second integration process. Okay? So that's multiple integration. I think I have examples here for triple integral. Oh, by the way, wait. This one is for limits which are trigonometric in nature. R, dr, d theta, meaning you are to integrate first in terms of r. So it's now r squared over 2. You are to substitute the limits 2 and 4 sine theta. So you will have 4 sine theta for r squared first, divided by 2 minus 2. That would be 4 divided by 2. This will be the answer. Okay, 8 sine squared theta minus 2. Then you do the next integration in terms of theta. This will require the identity equivalent. That way you can integrate. I will not discuss that anymore because we're done with the integration part. But as to the procedure, this is how it's done. Do the first integrate from the inside going out. Okay? For triple integrals, class, it's the same thing. You just start from the inside going out and substitute the limits before you go to the next integration process. So I have here an example. Very simple example of a triple integral. First is in terms of z, so you will have 4xyz squared. Limit is 0 to 1. So you just substitute 1 for the z. So that would give you 4xy. Then you go to the dx and dy. So dx, that would be 2x squared y. 2x squared y is a constant. Limits is 2 to 3. Substituting x, that would be 8 to x squared. So that would be 2 times 3 raised to 2, that would be 9, 18 times y. And then you substitute this 2 as well. So this is your corresponding answer. Let me check on this, huh? Sorry. So you will understand. We annotate. So you have this and you substitute 2 and 3 to x. So firstly, you are to substitute 3. So you have 3 squared y minus, so you substitute 2, 2, 2 squared y. So you will have this as 9, 18y minus 8y. That is why you have 10y. If you integrate this will give you 5y squared, limit is 1 to 2. So you will have 5, 2 squared minus 1 squared. So you will have 5 times 4 minus 1. So that will be 15. Let's see. 15 for the integral, for the answer of this triple integral. I did not include it anymore. There you go, 15. Okay? You can have this also, but just start from the inside going out. I think I've placed here 2 more examples, so I leave that to you to read. Anyways, we're just concerned with how you do multiple integration. Now, any question? Any question, class? My time here is 4:34, but I can cater to your questions if you have any. Anyway, the process of multiple integration without the application is very easy. It's just like doing the evaluation of uh, an integral, but you do it several times because you have to integrate not just once, but twice or thrice. If you have a triple integral, the application is in finding the volume of a particular solid. If you have a double integral, you're interested with the area of the region. Now I won't discuss anymore the applications because that would be very already heavy for you. You have questions, clarifications? Okay. But nonetheless, class, if you go through the recordings of this and you have questions, don't hesitate to ask me. Okay? Ask me questions if it's not clear to you. That way I can help you out.